So just to give you a bit of an introduction to who I am, so my name is Jordan McDonald, of course, and I work for Kainos in the Applied Innovation team. So a lot of my experience, in particular with Kainos, is in the field of artificial intelligence. Sorry, artificial technology is definitely not a real thing, but should be, I feel like. So this started actually at university, where I got an introduction to a lot of classical machine learning techniques, and it's continued throughout my time at Kainos, where I've got a feel for different things on deep learning and TensorFlow, and a lot of different topics, which have been pretty great. And it's given me a lot of good things that I could do around education and teaching people, which is probably the most rewarding part of the job I've had so far. So a bit of context behind this actual talk. So Airbus have released a Northern Ireland challenge to use their space data for this particular theme on sustainable living. So Code4Good, who are the organisers of this, sponsored by Kainos, of course, I've ticked that box, I don't need to say it anymore, have saw as an opportunity to do a hackathon using the Airbus dataset that they're providing for the challenge. So this lecture is going to take you through using artificial intelligence to classify different objects in a space image. There's a lot of challenges around this that you might not expect are really hard, and you might think the machine learning is the hardest part, but actually that's the easiest part in this process, and hopefully I'm going to demonstrate why. So I'm going to walk you through from a space image to a prediction in the space of, I guess, 40 or so minutes. So a lot of this is going to be hidden behind the wizardry of PowerPoint, but I think it gets the point across quite well. So just a bit of a refresher on the hackathon details. Of course, the lecture is happening today, and the hackathon itself starts on Friday. So if anyone here is not signed up yet, please do. I know there's still spaces available. And I'd hope to see you there. I'm providing, I guess, a bit of a technical reference for the presentation itself. So I'll be there on the Saturday, making sure everything's going well and trying to offer as much advice as I can. So some of the goals for this presentation, it's a very stereotypical way of starting every presentation, but I think it's quite nice. It tends to frame things around a few key ideas. And if we achieve these things, then that's pretty great. I see that as a win. So introduction to machine learning. This is going to be very, very, very basic. I think I need to add times 100 to the very part on the basicness of this machine learning introduction, but I think it does the job. It gives you just enough to understand the core principles and use the tool that we're going to provide later, but a bit more detail on that as it comes up. So the most important part of this presentation I see is space data problem selection, particularly in the pre-processing of the data, and that'll take up the bulk of everything that I'm going to talk about. Space and how to work with the images is actually still very immature. So you have these big companies like Airbus and so on, but they don't make it easy to use the space data. And that's a constant theme across the entire industry, and it's still a bit of a problem. So I'm going to try and make that as easy as I can. So if we tried to use space images for the hackathon and just gave you them as they were, I don't think anybody could get anything done. So it's been a lot of work to make it a bit easier to use. And third, to show you a bit of image classification using a vision tool that's actually built in Kainos. So I actually co-built this program alongside one of my colleagues, Matthew Fitch, who some of you might actually know. And we're actually going to open source it for hackathon, which is pretty good. And it makes your life a lot easier if you want to do some simple classification-based stuff. Okay, a bit of an overview of machine learning. So it's one of those things that can feel really distant or on the horizon, but it's actually here right now. And a lot of companies and academics are doing some really amazing things with it. So in the past 10 years, tools and hardware have matured to the point that guys like us, software engineers, or whoever it might be, can actually do a lot of things in machine learning quite easily. The support and the tutorials are actually pretty good now, not perfect, but it's getting somewhere, and now is the time to strike if you want to get into it. And this is really reflected into the publicity and the acceleration of progress of machine learning in particular. So in the past few years, you've seen advancements every other week, it seems like, and it only seems to be getting faster to the point that I can barely keep up now. And given that's my job to be on top of this stuff, that's a bit of a scary thought. One thing I always like to say is kind of a fun image to put in your head is there's actually more computational power in your phone than there was that took the astronauts to the moon. And that's actually pretty scary. And that rate of progress is never going to slow down. So you might think, how does this even affect my daily lives? So a good example I always refer to is actually Google. So almost by stealth, they are essentially a machine learning first company. So every product they have is built with machine learning from the ground up. So you imagine their search and their various services they provide. And this is a good example to follow if Google are doing it. I think they know what they're talking about. So we'll start with a wee basic example of machine learning used in a really intelligent way. This showcases machine learning being injected into an existing service and making it a lot better or a lot more productive. So I'm sure everybody here has heard of Airbnb. They just connect people for homes to stay in, so it's quite simple. You'll see in 2014 there was actually a bit of a boom in the amount of people who started staying with Airbnb. So what was things like before this? What was the service actually like? So they used a lot of basic signals for their search parameters. So you go in, you specify a number of rooms, location, all that good stuff, all really basic and uniform to every guest, which is the key point here. If it's uniform to every guest, there's definitely no machine learning going on. But in 2014, they integrated something they've been working on for a while, personalized search results. And this used things like computer vision to be able to detect the decor in rooms and in houses that you quite like based on your past history. And based on this, they integrated their search results, changed the rankings, and found out a lot more people stayed with Airbnb with this preferences built in. They also added a few different things like predictive pricing. So imagine if you're going to a conference in, let's say, Hamburg or somewhere like that, Airbnb actually knew this and they will jack up the price based on machine learning as one of their key signals for price prediction. And that's pretty good. It's a real life example of how machine learning has actually changed something for a company. So, bit of fun, I guess. So this is probably the most nerdy introduction to machine learning you'll ever see. So I actually got started with a data set of Pokemon, and I don't think anybody's really done this before, so hopefully I'm the first. So machine learning starts with data. Your results really live and die on the quality, the quantity, and the volume of your data, especially when it comes to noise, missing values, is it labeled, is it not labeled, and especially human error, which could throw things off completely. And the first phase of every machine learning project should really be a data science step. You should be evaluating your data, looking for a lot of key signals that you think are important, and giving yourself some evidence for even approaching a machine learning problem. A lot of the mistakes people make is, well, let's just throw machine learning at this. And I kind of get the sentiment behind that, but if you do that, you're setting yourself up immediately for failure. So in this case, back to a bit more fun stuff, we have our dataset Pokemon, and this is one I actually made myself. I didn't pull this from the internet or anything. I actually downloaded it, made myself, as in I downloaded a YouTube video, wrote a Python script, chopped every 30 frames up, saved them into a dataset, and there you go, I have every Pokemon as an image in the space of half an hour. So that was pretty fun. So say in machine learning, we had this really trivial goal if we want to categorize the different Pokemon into the different types. So say we wanted to take all 700 Pokemon, say we know how to figure out which is a fire type, which is water type, which is a leaf type. So I'm going to take you through, based on this example and this goal, how to build a really simple machine learning system. So I'd imagine if you know this data set quite well, you can imagine colour is quite a big indicator, and there's a bit of a hint there in the free dev picked. So for vision systems, that's quite apt. But we're going to try and approach this from a bit more of a multi-feature perspective. So you imagine we have a Squirtle here, and he has a bunch of different features that are associated with him. So these are things essentially which identify a Squirtle as who he is. And that's things like the primary colour, his height, what he's effective against, and his ability. You notice I picked ones that are actually quite relevant for this problem, and I think the last one I actually made up. I tried to get that off the Pokepedia or whatever it's called, and I don't think it was really reflected my example, so I thought I'd just change that. So let's expand this base data set to a bigger problem. We have every Pokemon is associated with these different features to make up who they are. So imagine our input is the entire data set, and I've put a few examples in there, and every data instance is associated with its type, which is fine. So if we get data in this form, where every instance has a type, and the machine learning model knows what the type is, this is supervised learning, which is probably the initial and first thing you're ever taught when it comes to machine learning, aside from the definition, which I'm not including this time for a couple of random reasons. So if you don't have this label information, that is actually unsupervised learning. So it's just the inverse. But this is often way more tricky to work with. When you're doing unsupervised learning, you're doing a lot of crazy stuff like clustering and grouping the categories based on the features. When I say it's more complicated, it's probably a side effect of me not actually doing that much unsupervised learning. So there's a bit of bias creeping in there. But for example, we will stick with this. So we've got our Pokemon, our images. We simply pass those to a really simple machine learning algorithm, which then we can use to make a decision in the future. So it's really basic, really simple machine learning example. And this, in a nutshell, is really how it works. But at the same time, it's not how it works. There's a lot of complexity and detail in this. It's actually quite important. And it's actually the bane of my life sometimes. So every instance, just to confirm, is associated with its label, just like this. And this, if we're trying to do this classification problem, that's how we'll pass it into the system. So we're not here to talk about Pokemon, of course. We didn't add that to the promotional material, so it took up a bit longer than I expected. So we're actually here for space images. So I'm sure everybody can guess where this actually is. If you can't, I'd be seriously worried about you right now, because I'm sure most of you actually live here. So that shows the majority of Belfast, bits of Newtownabbey, bits of Hollywood, bits of Bangor, and that kind of thing. And this is what a typical satellite image actually looks like. It's essentially a bird's eye view of the world. And what makes these different from standard images is they're very, very detailed. Again, I showed very times 100. I could zoom in on this image to the extent I could go right into a car and see its colour and potentially even see the people inside it. People on a solid image tend to be 1 pixel. That's how detailed these things are. But this is great, you might think. We've got like so much we can extract from this, but there's actually a lot of downsides to this kind of image format. And I think it's actually quite bad. And you might disagree with me and you think this is a rich source of quality data and information. You do things like car park detection, change monitoring, coastal erosion, the list goes on and on. But we need to consider what's actually practical in this scenario. This won't integrate well with any system, never mind a machine learning system. So I actually did an experiment where I tried to load one of these images into GIMP, which is an image tool, of course, and it just crashed every time. So not only are these images bad to work with, they can't be used by a lot of different programs because a lot of computers don't have enough RAM to handle images of this size. But a bit more on that later. So one of the key issues, if I try to formalize this a bit more, is the huge resolution, and that one's pretty clear. A common space image is around 30,000 by 30,000 in resolution, and that's absolutely bonkers. And this means there's a key pre-processing step that really needs to be integrated to make this actually sensible and easy to use. So another problem is, imagine you're given this image, and you might think, and someone might say to you, try and do something interesting with this, say in a hackathon type scenario, you might think, I don't even know what to do with this thing. It's just so abstract, it's so zoomed out, there's no way of correlating this with useful things you can work on. So this is where problem selection comes into this, and that's actually by far the most important thing. And I'll spend quite a bit of time on that. And our point is, what insights can you extract from this image? It's actually quite a lot, especially if you consider things over time. So satellites don't give you complete real-time coverage. A lot of time you might only get a new update every week, but this might be enough for a lot of big macro problems. And I'll go into an example of this later. And the last question. So I guess the answer technically is yes to this question, but only do this if you enjoy your laptop freezing and potentially come the blue screen of death, because it actually scared me when I tried to do this. So now we've discussed some of the fundamental considerations before we even start on the problem. So we haven't got to the fun part yet, we haven't even started with the amount of stuff we've had to think about. Let's introduce the data set I'm working off. So these are essentially satellite images of a couple of bay cities. So that sounds like a rock band or something like that, I'm pretty sure. So the first is San Francisco, and the other is one in the Middle East, whose name I keep forgetting because it's actually way too complicated for me to remember. So I'm going to give you a flash of the entire data set. Just to remember, this might not seem like a lot of images, but these images are actually huge. So as they go through, have a think about the sort of things you could extract from this. It's a particularly biased example in a lot of ways. There's one obvious object that stands out here, but we'll go with it anyway. So what problem did I actually choose based on this data? And it's actually quite obvious given the spoiler of this talk's title. I wanted to focus on the ships. So we needed to find one categorical thing that was consistent and stood out and really fit with the resolution of these space images. So can we actually get some useful insights and extract some knowledge from this? But we need to do some validation. This might seem like a really stupid example in a sense. I don't blame you for thinking that. But who would this actually be useful for? Would it be valuable for anybody? Well, you can do a couple of different things like monitor port activity levels, supply chain analysis. You actually track the ships, and you can track the thing you have on the ship en route to your country. And it would be quite good for tourism, tracking cruise ships and that kind of thing. So there is a few useful ways this could be applied. So that's great. We have our actual problem, so that's good. So I'm going to use the rest of the presentation to take you through how we actually get from this. We've got our problem, we've got our images. I think we do something useful. But first, there's a couple of top tips around problem selection. And this is something that's actually quite tricky. So I implemented the first of its kind, the world first red system. So, and I chose this because the acronym kind of works. And it is a real acronym. It's actually an initialism, which people do to make a mistake for, which is kind of annoying, but it's a grammar thing for me. So the first is resolution. This simply refers to the amount of detail in the image. Everybody knows this, so that's fine. So if you're trying to detect cars, your solid images need to have enough resolution for that to be suitable. Enough samples. This is really the bare bones of machine learning anyway. If you have enough data, what's the point? And you need to have distinctive visual features. Does it stand out from the background? In our case, for the boats, yeah, they kind of do. They kind of like, jump out at you, and their background is actually just things like water, which is quite easy to work with. So once you tick all those boxes, then you move on and start doing something interesting with your data. But if you don't, I would probably say don't waste your time. So you might think this is a bit on the nose to make the red system associate with the letter red. So I'm going to actually change that because I don't think it's a bit too cheesy. Going from Pokemon to something like that's too much, I think. So when I say resolution, I really do mean spatial resolution. This might feel kind of weird, but the lower the resolution, actually the better it is. So when I say spatial resolution, this means the amount of detail in a pixel. So if your spatial resolution is 50 meters, that means one pixel is 50 meters. If it's 10 meters, one pixel is 10 meters. And that one is definitely a lot better to work with. I'd rather have 10 pixels for my boat, or I'd rather have, I guess, 10 pixels per pixel for my boat. It's a bit of an Inception style thing going on there. So that's much easier to work with, a lot more features we can get, which is great. So here's a difference between a 10 meter resolution and a 60 meter resolution image. It's pretty obvious why one is not suitable for something that's very fine grained. So 60 meters might not be great for things like detecting our ships or detecting cars, but it is good for some macro problems. Say for example, for whatever crazy reason you want to detect bridges, that would be enough, and you don't need that extra detail. But in our case, 10 meters is pretty spot on. So you can see already there's a lot of building fidelity that's been lost, and you barely make out the detail on the bridge. And it's a good thing we have the big screens here, because I think it makes it quite obvious, the difference. Okay, now so enough samples. This one's pretty self-explanatory, really. So you need a data set of positive and negative samples. You need your things that count as your ships, the things that don't count as your ships. This could be the water, it could be the port, it could be anything that doesn't particularly matter. But there's no data instances to work off, then again, what's the point? For a minimum guide, I would say if you could find 25 of the object you're trying to get, that's okay. There's a lot of things you can do in the back end to make it a lot more big and robust, particularly around data augmentation and things like that, which our tool can be tweaked to support quite easily. So for the hackathon especially, it's not really suitable for working with large data sets. The biggest I would go to is probably what I'm working with, which is 200 per class. So we have 200 ships and 200 things that aren't ships. Really what you want to do is focus on your concept and your story. If you get enough data to prove that what you have works, that's all you need to do, and that counts as a win. Of course, distinctive features, this one is pretty self-explanatory in our case. With the ships, I think it'll become quite clear in the next slide why they are quite distinctive. So you need to think about the features, the water background, the consistent color, the size, the shape, textures, curves, and so on. These are things that really the machine learning model in the back end is really trying to detect. So if you can detect these things, then great, so can it. There's a good example where I think a company based in Northern Ireland, POFXL, they've got results that are actually better at detecting heart issues than real doctors. And if you can do it, the machine learning process can do it, especially if you give enough data. So these are a few crops that I took out of our space image. You can see if we apply our REDS qualification system to this, the ships are quite distinctive, which is good. We do have enough volume, because I stated that before, and the resolution. So based on these crops, is that enough detail for us? Yeah, I think it's pretty good. There's definitely enough there to detect a ship, which is great. So our machine learning model will definitely do a good job, and it will thrive, which is pretty great. So the big question, and the one that was probably the most hassle in preparing the data for this upcoming hackathon. You won't believe how long was spent on this, the amount of dedicated man time. There's people I could look at who spent a lot of time on this in the audience right now. So without a well-formatted data set for machine learning, there's no point, of course. So we've seen that the space images are completely unsuitable. There's a lot of ways we can make this better. And the first is essentially the slow way. And there's no way, and we definitely don't get faster than slow. Things only get slower from here. So there's 3 different techniques I've put together, and I think they're pretty good. By pretty good, as in they'll work, and they're things I've made up off the top of my head. So there could be better ways to approach this problem. So, bit of a reminder, what we really want to do is turn our space image into this. And this is perfect for machine learning. We just need a folder containing crops of our ship images and a negative class. And the negative class in this case could be really anything that doesn't contain ship. So that's fine. So this is not ordered or structured, and it's really just a bucket that contains our data. And that's the simple way to think about it, and I won't go too much detail on that. So if you want to do this, there's one tool. I think there's only one tool at all that can do the job here, and that's QGIS. So what's a GIS tool? It's a geographic information system, and these are tools that are actually quite good at handling large images and map coordinates, which your data will come with, and you definitely don't want to lose the coordinates. There's absolutely no point in a crop and using the coordinates of the image itself, because that's pretty pointless in a lot of ways. So I was actually talking to an Airbus engineer, he's the R&D manager for the entire UK for Airbus, and this is a tool they actually use, and it's completely free, so that's great. So what I'm going to show you is 100% a very manual process, but I will recommend this for the hackathon. While it might seem slow, doing an hour, get your data set and do this right is definitely the right approach. But you might be a bit ambitious and try and do something a little bit crazier. In that case, I won't discourage you too much. So what we really want is to transform our crops just like that. And I'm going to give you a bit of an overview of the tool that does the job. So I'm going to kick into a bit of a live demo, and we'll see how we get on. Okay, so here we have QGIS. So for the hackathon, we do provide support in terms of how to set this thing up and how to use it, so don't worry about that. And a lot of the detail around how that happens, I'll get into a bit later on, because we have provided a pretty comprehensive README, which goes into what's important, how you set it up, and that kind of stuff. So what you want to do, if you have your satellite images, and we will give you quite a lot for the Airbus hackathon coming on Friday, we want to load in our space image, which is definitely that one. So it'll take its time to load in, because after all it is pretty big, so bear with it. Okay, that's not great. Okay. Yeah, so do you want to know what happened there? This is actually a lesson of what not to do. So QGIS is actually frozen because of I tried to load the XML file instead of the image file. So I'm going to quickly correct that. So this is the ultimate how to recover from a failed live demo tutorial going on here. Okay. So QGIS. Okay. There it is. Okay. Phase 1 recovery is complete. Now we're on to phase 2. This is cross your fingers here, this is bold stuff. So what we want to do is load our QGIS tool once again. QGIS. So do you remember when I was telling you about why space images were bad? Well, I think this sums it up quite a lot. Okay, QGIS is loading up, and then I'll get back on track. Okay, there we go, that's pretty good. Okay, good, we didn't get the bump that time. I didn't want to burst someone's eardrums again. So what we can actually do is load this image, which will be pretty good. Okay, we've got the wee spinny thing, it's working. This is great, we're back on track. Pretend that didn't happen. So it'll take a bit of time. The image is around probably 4 gigabytes in size. So this wait time is completely expected, and there's not very many tools that can handle this. So here we go, it worked. So we do a few interesting things here. The image is of course very detailed because of its size. So what we do is zoom in on something of interest. So say for some crazy reason, I want to have a beach detector. So let's zoom in on the beach. Even the action of trying to zoom in the image causes it to freak out a little bit, but don't worry about that, that is perfectly expected. And I have tried, there's no tool better at this than the one I've found in here. So say we've got our beach and we want to train a beach detector. What we can do is then perform our crop by going to extraction, go to clipper, and then we can just do something like that. So what this gives us is not only the crop, but also the coordinates from the entire image. And this is pretty important if you want to do anything sustainable or really interesting, beyond simple object classification, you do want to keep your coordinate information. So once you've done this, then we'll select our output file. So important point here, for the hackathon, the file format you will be given is a JPEG 2000. This is a very specific format of JPEG, which is perfect for handling images of this size. And it's good for handling coordinate information and that kind of thing. So we need to output in that format as well. So I'll just grab it, and let's give it a really boring name, like 1. And then we just go to save, and then, okay. So once that finishes in about 10 seconds or so, what it'll actually give us is one cropped instance of our data set. So you might think, am I crazy for recommending this for hackathon? Kind of, but believe it or not, this is by far the best way to do this. So it's actually complete, and I've put it on the desktop and been doing some verification steps. Yes, I do. Okay, so we've got that sitting on our desktop, along with an XML file which describes its coordinate system. So that's great. So then we put that in our bucket for our data set. So you remember I showed that folder system before of what we do want? Just dump it in there and then it's job done. And the sad fact is, if you do want a data set, and I did recommend 25 as a number, you have to do this 25 times, at least 25 times. So while it's not great, spend an hour in doing this and doing it right, I think pretty worthwhile. It's a good trade-off. Okay, we'll jump back into the slides. See you later. Okay. All right. Great. Okay, so that's the slow way for data set creation, but let's go into the slower way. But it's actually quite a bit more ambitious than what I just showed. And while I don't recommend this, I think if someone for the hackathon actually did this thing and wrapped around a pretty good use case, I wouldn't be surprised if you win. And if you did this, I'd pay you money to take it off you, because this is something that would be very useful for a lot of companies, especially if you put it on GitHub and open sourced it. This will get you quite a lot of stars, I'd imagine, if you're into that kind of thing, I guess. So the second way is a marker-based approach. So what you can do is create this GUI system where you can load in the image, and that's going to be quite tricky because you need a streaming-based approach, not something that's a mass dump, or you have the crashing issues, of course. So good luck researching how to do that. So what you can do is you can label the objects of interest with, say, a red dot, and then you can click go or whatever you want. And a Python script in the background will do the crops for you just based on this one simple marker. So this is a pretty nice way to do data set creation, especially for the space images. And get away from space images, if I had something like this for machine learning where I could output bounding box information, I'd bite your hand off and I'd take it off you right now, because that's something that'd be pretty great for stuff that I'm working on, even in my free time. That'd be pretty good. Okay, data set creation, the other slow way. So there's a pattern here where every way is particularly slow, but this is the nature of the beast, and you just have to accept it. But again, it's better long term. So this approach involves doing essentially what I call a naive crop of the entire image. So what you want to do conceptually is to break the entire image into a grid. So if you can do this in a Python script using what I like to call a sliding window approach, you can create your data set with one script quite easily. But there's still usual problems of RAM issues and trying to stream in an image rather than just a bulk dump. And it will take a long time. Bulk dump is quite a good image if you think too hard about that. So sliding windows, this idea, it's quite heavily associated with classical machine learning. And it's something that I've used before back in university for pedestrian detection and things like that. And I think it's quite an apt approach for this if you decide to pursue this. I think this is by far the worst way to approach the problem, but still a possibility, and it's worth including this as a way to inspire ideas. And if someone thinks of something better, by all means, tell me, because you'll be doing me and a lot of other people a big favour. So how this works is you put a window on the top left corner of the image, and then essentially what you do at each interval, you just do your crops, just like that. And as you can see, if we keep doing this, our data set will continue to build up, and then we can select the object we want to try and detect. So it's pretty decent, and it'll do the job, but again, it'll be quite slow. So this will continue until you scan the entire image, which is fine. And then you keep going until you're complete. So you do this for every space image. And I actually tried to do something like this in my free time. I was prepping the data for the hackathon on Friday, Saturday, Sunday. And for one space image, running a Python script that did just this, took 3.5 hours. So don't do this. Okay, so this is what success looks like. If we can get our data set looking just like this is a win. And that's perfectly ready to be used in the machine learning tool that we're outsourcing or open sourcing for the hackathon itself. So right now you see all the different images in the crops. They're actually unsorted, and it doesn't particularly matter at this point because we're going to clean that up a bit later on. So the question you might think is, based on our example earlier using the Pokemon dataset, is do we need to label our images in some way? How can we teach this machine learning program to actually understand the content of the images? Well, we definitely do, and we really need something like this. We need to sort it into what are ships and what aren't ships. And that's what the KNOS vision processing tool is going to do for us. So for the hackathon, as I mentioned, we're going to completely open source that to give you instructions on how to set it up and how to use it. It's actually pretty nice for simple problems like this. So given the experience of 10 minutes ago, cross your fingers. I'm going to do our live demo. So let's shift across. Okay, I double clicked there, make sure the crazy noise didn't come again, so that's good. So we have here an example data set of things that are currently untagged. So this is essentially our bucket of images. So there's a bit of an artifact thing going on here where I've done a lot of work in the background before showing you this, but that'll be fine for now. This is good for demonstration purposes, of course. So we can do a couple of interesting things, like do an upload. Just like that. And there we go. The image we upload is now a part of the tool, which is pretty good. And this works on bulk, so if you have a big data set, you can just dump them all in, which is pretty nice. So what we can do for our tagging process is click on the image we just uploaded, go to vision processing, and we can tag it as a, what a surprise, a ship, of course. So you can do this for every image that you upload, but doing one by one is a bit of a pain, of course. What we've built in is the functionality to do this all at once, almost. So you do things like this, where you can drag a bunch at once, which is a bit nicer to work with. So that's fine. So let's evaluate our current state of the tool. So let's look into the type of tags that we have, and we've already labeled. So in advance, I've labeled all these as not ships, and you see there's quite a lot to the extent there's about 200, I think just over actually. We have our untags, which we just saw, and we have our actual ships. So this is really good. We have a nice data set. It's actually pretty perfect for machine learning. This is the sort of stuff when you're learning machine learning, you actually get handed to you on the plate, and a lot of that hard work is not done for you. And a lot of that hard work is where the real value lies. And in space images, you're definitely going to get practice at that. So let's jump back to the tool itself. And what we can do with this trained data set is we can train our machine learning model. So we can build some intelligent insights and be able to make predictions and classifications and all that good stuff. So let's kick it off. So this is using all 400 of those images to train our model, and then we can do that for a lot of future predictions. And it won't take that long in the grand scheme of things. It'll take around probably 10 seconds, which isn't bad. And just like magic, we have our model in the back end saved, and we can just use it immediately. So say I want to actually classify all these things. We're not going to train anymore. We're actually going to try and make a decision based on our machine learning process, based on the data we gave it. So let's see how it actually does, and fingers crossed it does well, because I did train it from scratch. And usually when you create a new neural network, which is the back end of this, the weights are randomly initialized. So fingers crossed, once again. A lot of risk in this presentation. So results are not bad, actually. They're actually pretty spot on, I think. So we've managed to filter out our ships pretty perfectly. I'm actually surprised by this one, since it's actually cut off, and I have no idea what this crazy wave structure is coming out of it. And the things in not ships, I think, are pretty good as well. This one's acceptable, I think. This is quite a blurry image, and I think if I got that wrong, we can't really hold it too much to blame. And this one's impossible, of course. We know that's probably a wee fishing boat somewhere, but we're not going to be able to detect that. So that's pretty good. And the tool is really just that simple to use. It allows you to label images and create a machine learning model and make a decision that quickly, which is pretty nice. And of course, I'll be around for the hackathon to help people out if they do wish to use this. So please do get in touch. Okay, now we'll jump back to the slides. Great. Okay, let's look at a bit more detail what actually happened there. That all feels very pie in the sky, I imagine. It feels a bit too abstract, a bit too hidden behind a user interface. So let's try and tease out a bit more of the detail. So we have 3 phases. We have the upload, the tagging, and the training phase. On upload, we just have on desktop or in a folder, just our images. And what we essentially do, when I say upload, that's really just a cheat word for I'm moving it from one directory to another. It's really just a copy function. So this tool really just works locally. So if you want to have a bulk data set, you want to move it into this particular folder, you just copy and paste, and that's something that's quite easy to do. Now in the tagging phase, we just separate out what's our ships and what's not our ships, and then we use this to combine our data set and train our neural network. So that's pretty good, and it's actually quite simple when you put it like that. If you imagine these as a set of Lego bricks which you're trying to put together. But that's the beauty of a useful, really simple tool. A lot of what's going on in the back end is actually fairly complex, but by all means, I encourage people to try and break it and to try and make it better, because that's what it's there for, of course. On the back end, there's a lot of quite interesting stuff going on around resizing the images, so they're all the same size. So you imagine when you're doing the crops, it'll be pretty tricky making everything the same size. So that's something we've tried to account for, so it makes that problem a lot easier. And it does things like applying pixel normalization to reduce dynamic range issues, so the influence of light and dark pixels and things like that. But I'm sure you'll check this stuff out as soon as you can. all the machine learning and a lot of this, I guess, magic is held in the one file. And once you have a look at it, you'll see all this is being done in about 200 lines of code. So it's quite easy to pick up and to change things. So for all the software engineers out there, I guess, who like to get a feel for a bit of a tech stack, I'm going to give you a bit of high-level overview of how this thing's put together. So front end is really simple. So it's mostly just bog standard HTML and JavaScript with just a materialized, lightweight front end. So there's nothing too exciting going on there, and you just do the things that I demonstrated. One thing to note though is our tool has only really been tested in Chrome. So this is a bit of a side effect of working in applied innovation. We don't do unit tests, and we don't particularly test things that well. We test on what we know works for demonstration purposes. I'm not saying it won't work on Firefox and whatever. Definitely won't work on Internet Explorer, which is dead now, thankfully. I remember the hell of my placement year trying to support Internet Explorer 8, which has made me cry a few times. So, okay, the back end. So we just have a Flask microserver, which just handles requests and response. And it's actually pretty straightforward. Nothing too crazy going on there. We're definitely not serving resources and that kind of thing from Flask, so it's quite simple. But the real star of the show here is actually Keras, which is an abstraction of TensorFlow, which is a library Google released about 2.5 years ago. And what Keras does is essentially turns TensorFlow into the ultimate black box. So a lot of the process of creating a neural network from scratch, you could do in probably about 20 lines of code as a series of just API calls. So this is good for a lot of different ways. It's good for software engineers, but bad for people who want to try and understand why things aren't particularly working too well, which I've been in the position of quite a few times. So I mentioned TensorFlow there, and it's a good callback, I guess, to the start of the presentation. I says the tools and services are actually maturing quite well. When I first used TensorFlow, it was version 0.3, and believe it or not, something that took me a week's work was actually figuring out how I could load an image to be used by TensorFlow. So tensors are a very specific array. They're a multi-dimensional array, and they're actually quite complicated in how they represent images. And I had to build an entire image loader process from scratch because TensorFlow's documentation or examples decided not to do it. All they showed was give you these sample datasets were already in right format. And believe it or not, to my frustration, about 2 years later, if I tried to do this again, I could probably do it in 2 minutes with a function call in Keras. So things do move very quickly, and they will continue to move that quickly. So if you think about the likes of Google's AutoML and Amazon SageMaker, that's almost another status leap forward for people like us who just want to use machine learning. Okay, so I've mentioned before I use neural networks on the back end, and this is a certain variant of neural networks called convolutional neural nets. So these first became popular, I believe, in the 80s. I think the idea was first coined in 59 in a research paper, but they first received widespread usage in the 80s for handwritten notes recognition and things like that, so basically OCR. And they're actually quite good in the fact they don't require any pre-processing, especially in the case of images. Usually in that example I showed before in Pokemon, I showed you the features, I showed you the things that distinguish what is a Squirtle. For convolutional neural networks, you don't need to do any of that, it does it for you, and often it can do it a lot better. I mentioned before that machine learning systems can detect heart disease better than doctors. It's because of techniques just like this. And this is really the bedrock for the deep learning boom that started happening in the past 5 years, probably. I can also do a lot of different things like facial recognition. So the iPhone X face recognition is actually powered by convolutional neural networks, and it builds a 3D mask of your face alongside various other sensor data. It's actually really amazing what they've done. I actually mean to look into it a bit more. And there's this challenge called the ImageNet challenge, which is essentially an object classification challenge. And for the past, I think, 3 challenges, the teams, they're all in the top 10 use convolutional neural networks. So if you try and connect the dots and think why things are moving so quickly in the past 5 years, it's mostly because of these bad boys, I guess. Another good example is AlphaGo. So they also use convolutional neural networks, but they use it in a very interesting way called policy networks. And what they have going on is almost the complexity of neural networks, but on steroids. And if you want to get a feel for, I don't know, potential suicide, then please read their research papers. Okay, I'm going to try and explain it really simply what's going on under the hood. And a convolutional neural network is actually this very difficult mathematical process. And there's a lot of things that are quite hard to understand and wrap your head around. So while tools make understanding this and using these things quite easy, I'd say there's a very small percentage of people in Northern Ireland who can actually explain them quite well. So I'm not going to try to. So I'm going to keep it very simple and very visual. So for simplicity, I'm going to make the image black and white. So as everybody here, I'm sure knows, images are made up of three color bands, the red, the green, and the blue. And these are things that are used by neural networks to come to decisions and get a feel for what a feature looks like. But for demonstration purposes, it's actually quite tricky to show because there's no way of me representing a 3D plane on a 2D screen, so I'm not going to do it. So you can really imagine an image as an array or a matrix of pixels, or to make it even simpler, numbers that range from 0 to 255, where 0 equals black and 255 equals white. So this is a bit of an artificial example where I've said this square equals 170. But in each of those squares, you'd imagine you can probably squeeze in 500 more squares with the actual pixel values. So bear with me for now. So what you do on your CovNets is you scan the image. And what this is use the pixel brightness values to try and find what it thinks are features. So on the neural network level, this just involves tweaking essentially a series of what are called weights between the various neurons. And that's a very simple way to put it. And if you have a lot of samples of the image, or the thing you're trying to find, these weights keep getting tweaked until it gives you an understanding of what the image looks like. So when you're training a neural network, you're really training weights, but that's not too important what that detail means. So the broad strokes, I think, for this sample are quite important. So this is not particularly detailed, but I think it does the job for now. So the type of features it's actually looking for are likes of color, curves, texture, the brightness values, recurring pixel patterns, things just like that. And it does so automatically with no real dev, I guess, tuning. And that's part of the black box nature of neural networks, I'm afraid. Okay, the vision processing tools, support and access. So we have provided a repository that's going to be open sourced, and the organizers will give you a link to download that, and you can fork it or you can do whatever you want with a bunch of set instructions which I think are quite comprehensive. I wrote it, I guess, so I hope it's comprehensive is one way to put it. So I'm going to show that now. So you will be sent this link and you'll be provided with this README essentially. And what it does goes through how to set up everything you've seen here today. So we're actually providing a virtual machine to handle a lot of the annoying dependencies and things like that are actually quite tricky around setting up the tool. But if you're a bit of a Python whiz and you're quite good at handling the dependency side of things, or if you know what Conda is, then you probably don't need to do this. But that's a bit of a cryptic hint, I guess. Shows how to install the virtual machine, and probably the most important thing for everybody here is getting this guy installed. For the dataset we're giving you, you will not be able to look at the images without this. And that's a bit of a sad fact. So I do recommend trying to install this in advance. If you try and open the images in some preview viewer on your Mac or Windows machine, it just won't show it. And that's just the way the space images are in this format. And we go into a bit more detail around how to actually prep your data set. So if you forget anything I've talked about, it just helps you out right here, which is good. Bit of project setup and a bunch of tips that I think are quite useful, such as how to reset the state of your model and things like that. So hopefully anybody who's going to Hackathon finds this pretty useful. And if there's anything missing, then I'm the person to shout out. Okay, so I have to do an obligatory Chaos is great slide. So I guess my boss is gone, so I can say, like every company, Chaos has its bad and it has its good. But in my case, in my experiences, mostly has a lot of good, which is great. And if anybody's a student here thinking of joining Chaos, the only thing I can say is by 2021, we expect to go from 1,000 people to around 2,000 people. And our AI capabilities is going to continue to increase as well. So if you're interested in this topic, interested in a good chance to getting a good job, then I think it's a good thing to go for. But that's enough for those tick the box exercises. It's like, okay, refresh. So Hackathon starts on Friday. If you haven't signed up, please do. I won't be around on the Friday evening, but I'm decided I might come around. And then on Saturday, I'll definitely be there. I'm thinking about being there on the Sunday. It depends how much people need me, I guess. I sound like Superman or something there. So there are just the details. I'm sure everybody knows these quite well. For more information, Code4Good's the way to go. And of course, thank you. So everybody's been really great listening to me drone on for 10 seconds short of 45 minutes. So I was aiming for 45, so that's pretty good. Just the last thing to mention. Keynotes are actually sponsoring the creation of a Northern Ireland artificial intelligence community. And that's something myself and Austin Taney from Analytics Engines are actually going to put together. And this is essentially, in a nutshell, is going to be a meetup group for artificial intelligence. We've got sponsorship from Digital Catapult, from Keynos, and we're going to put on a bunch of events quite soon. And if it's something you're interested in, please do keep your eyes open for it, because it'd be great to see everybody there. So thank you very much, and I guess if you think I did a good job, you can clap now. Okay. Okay, so everybody's feel free to move or leave or ask me questions, but I'll hang around up here for a while.